Hi roboticist! We are approaching the end of the modeling of our cobot, 6-axis robot with a gripper as well, and with modeling in URDF and set up all the joint controllers and tuned the PID values for each controllers. So this will be the end of this series of video for how to set up a ROS controller for your custom robot that you have modeled directly from scratch. And before dive into it, make sure to subscribe to the channel if you like this video and turn on the notification bell in order to do not miss the next topic. So now let's start. First of all, we are going to complete our robots, and to do that we need to add the link 5. So you need to go to the URDF file and uncomment for simplicity the transmission tag of the joint that links the link 4 and link 5. Then you need to add the joint 5 position controller, and always keeping the same type of controller that is gonna be, remember you, Forward controllers joint position controller. And of course you need to update the joint name that is gonna be link 4 _link 5. Of course you need to uncomment the description of the link 5, this is going to be a cylinder, and the joint as well. And finally you need to update, as always, the arguments of your controller manager node. So now we have everything set up, and we can spawn our robot by launching this launch file in our gazebo environment. And here we go. You can see that the link 5 is correctly spawned at the edge of the link 4, and it has a position horizontal, and if you press play you can see that all the robot stands. So what we can do now is to check the PID value of our joint 5 position controller. And to do that, as always, we are gonna add to the topic of our RQT GUI the joint 5 position controller command topic, and the type is going to update automatically. Then just set up a little bit better all the windows in order to do not mix up information and see everything that we need in clear mode. So add the frequency at 100 as always. And let's set a command value of 90 degrees, so it's gonna be 1.57, and you can see that the link 5 is moving correctly. Let's try again at minus 90 degrees, see what's happened, and is turning correctly, so he's doing what is supposed to do. So as always, we can plot the joint 5 position controller command slash data topic and make a comparison between the state process value topic of the same joint. So let's add to the plot graphic the command data, and now is set to minus 90 degrees and is stand at that position. And let's check what is the actual value by plotting the state process value topic. Let's add, and you can see that of course are overlapped. But as always, if you want to challenge the good choice of the PID value of your controller, you should send sinus values to your command topic with the amplitude of 90 degrees. So let's do it, and if you press enter, you can see that there's gonna be a step disturb provided by the command data, and in a few milliseconds the real joint position represented by the process value topic reach in a few milliseconds the command data. So meaning that the default PID value are correctly set up. So let's challenge the controller of the joint 5 position controller, and let's increase the velocity of the command data by 3. And you can see that there's always the step disturb, and as always near the 0 position there is very little misalignment between the process value and the data that we are sending. So, and it seems that this error decrease if we decrease the velocity. That's normal, because the more speed you want to send to your joint, is more difficult to the joint, to the hardware itself to follow accordingly. But you can see that for example, if you increase a lot the velocity of this command data, this error increase. So we could set a little bit better the PID control of the joint position controller. And as we did in the last videos, we are going to use the dynamic reconfigure toolbar. So let's looking for the joint 5 position controller. Let's click PID, and here are the values that we have set up for the joint 4 position controller, and we just copy and paste as a first guess in our configuration file. But let's see what's happened if we increase the derivatives value to 200. Okay, the error increase, so this means that it's not a good choice to increase the derivative value in this case. So for the moment, just keep as 150 the derivative values. Or better, let's decrease a little bit. So let's try to increase the velocity and see what's happened, and you can see that the error could be considered as negligible, at least for the joint 5 position controller, with this set of values P, I and D. So we can update the configuration file for the joint 5 position controller. So what we're gonna do now is to make a summary of all the joint position controller that we have tuned before. So it's gonna be joint 5 position controller, a joint 4 position controller, joint 3, joint 2 and joint 1. And for each joint position controller we are gonna plot the command data and the state process value topic in order to have in only one windows all the behavior of all the joints and how all these joints have been tuned. So first let's add all these curve to the matplot. And now joint by joint let's activate the expression for the command data. So the joint 5 position controller is already activated. We have add the joint 2, then joint 3, and you can see that the link are moving accordingly. Then joint 4 position controller, and finally the joint 1 position controller. So all the robots is moving right now, and this robot that we are simulating right now has 5 degrees of freedom, because the 6th we are going to add in a moment, that is going to be the TCP connector. But you can see that all the process value and the data have been well tuned despite the high velocity that we have set up as an expression to the command data for each joint. And this can be considered a good milestone in the ROS controller journey. And I suggest you to take a moment to see how this robot behaves, if the process value follows the command data for a few seconds to see if everything works good and fine. And I think that you can admit that is very satisfying to see all our job that has a completion. So let's close this simulation, and now what we're gonna do is to add the TCP connector and the gripper as well. Here we go. We came back to our URDF file and configuration file, and now what we're gonna do is to add the TCP connector and the gripper as well. So we have uncommented the TCP connector and the joint, and we have add as well the joint 6 position controller that is going to revolute the TCP connector to the link 5. And before to spawn the gripper as well, let's check the behavior in the simulation environment of this last joint. So spawn the robots, and you can see that at the top there is the TCP connector that is put in the horizontal way. And if we press play, we can see that the TCP connector is acting very weird, despite the fact that we didn't send to that joint any command data. The reason is that we have set a PID value that are not appropriate for this particular joint and this link. So, but keep calm and let's stick to our plan. And we are going to use the same approach as we did in the previous video. So first we're gonna send a value to the command topic that this time we can start as 0. So the command data is receiving a 0 value. Now let's plot the joint 6 position controller command data. Okay, it's 0. But now what's happened if we add the joint 6 position controller state process value? We should see something weird. And in fact the state process value profile has a profile of a saw, let's say, because it's going up and down without any control. So we're going to solve this by tuning the PID value. So let's try, for example, to avoid the derivative value and see what's happened. Apparently nothing happens, even if we delete the integer value. So now let's decrease the proportional value, and you can see that everything is fine now. The process value is overlapping the data value. This is what we should expected. Why that? Well, because the TCP connector, or better, the link that is attached to the link 5 has a less inertia with respect of the other links that are heavier and have a higher inertia. So commonly we can see that is not recommended to put as a first guess a higher value in proportional control, because otherwise the joint is acting weird, and it seems that we are losing the control of that joint. So let's set 90 degrees with this set of PID values. You can see that after a step disturb, the process value follows very well the command data. And the same behavior you can see that we have obtained for minus 90 degrees. So now we are ready to test the oscillation expression of the command data or the command topic, and we are sending to the command data topic a sinus variable with the amplitude of 90 degrees. And you can see that it follows very good. So meaning that the error is negligible, and let's visualize better by rescale the y-axis in the range that is of interest for us. And okay, there's the same graphics, the two curves are overlapped. So we can make a sensitive analysis. For example, if you put 50 as derivative values, you can see that the let's say, profile of the process value is appearing. This is a good example that proves that in this case, for this link and for this joint, adding a derivatives value decrease the quality of the control. So we can keep a value of 10 for the integer, and now update the PID values for the joint 6 position controller directly to the YOM file. And this is the robot how it looks like. Okay, we are getting closer and closer to the end of this series of ROS Control. What is missing now is to spawn the grippers and tune those joints that this time are not revolute joint but will be a prismatic joint. So the edge of the gripper is sliding on a surface of the TCP connector. And here we go. Now what we need to do is to uncomment the gripper right link and the TCP connector gripper right joint, and the same things for the gripper left and its joint. And then we need to uncomment the transmission tag for the joint that links the grippers left and right to the TCP connector. And then we need to add or better update the configuration file by adding the gripper right position controller. We can call it like this. Of course, we need to update the joint name, that is going to be TCP connector _ gripper right. So for the moment, just keep as always the same convention of naming every joint and every position controller. So then copy and paste for the grip left position controller, and for the moment just keep the PID value as is. We are going to tune later on in this video. And then for last, we can finish our launch file by updating the arguments of our controller manager nodes. So at the gripper right position controller as well as the gripper left position controller. Okay, we have finished and we have everything set up to test this final robot in our gazebo simulation. So ROS launch, name of this launch file, and here we go. We have correctly spawned all our robots that we have previously designed in our URDF file. We have tuned all the joint with the exception of the grippers right and left. So if we press play, let's see what's happened, and you can see that the gripper right is not going to the right position, and everything is it seems to falling down, but it's not falling due to the controller setup of the previous joint. Okay, so we can continue our approach, and so we can send to the grip right position controller a value or better an expression of 0, and you can see that the gripper right link is acting weird, and we have seen before with the TCP controller. This means that the PID values are not correctly tuned for that kind of joint and that kind of link. So if we wanted to figure it out how far we are from a good tuning, let's plot the gripper right position controller command data and the gripper right position controller status process value. And let's see what's going on. Okay, you can see now that the state process values has a wave behavior, even if the command data is set as an expression of a set point, 0 position. But besides that, the state process value of the gripper right position controller has a misalignment, or better, has an offset of round about 0.03, and another problem is that is acting as a wave, and this is something that we don't want to happen. So let's try to see how the changement of the PID value affect the state process value control. So if we increase a little bit the proportional value, well, the effect of the wave is increasing, so it's not considered a good choice. So I would increase a lot, but what happens if we increase a lot? Well, it seems that we still have a wave profile, but this time the state process value is getting closer to the common data value. So meaning that it could be considered a good choice to increase a lot the proportional value of our PID controller of the gripper right position controller. So let's try to make a set point of 0.05, and the process value follows correctly the command data. As you can see, if we go from 0 to 0.05, which I remember you are the lower and the upper limit respectively of your gripper right, and yeah, you can see that it seems that with this set of PID value the grippers act correctly. So we have it seems that we have found our PID value, and let's update it directly to the YUM file. And of course, since that the gripper left is going to be the same in dimension, at least, as the gripper right, we know already somehow the PID value that we need to put for the gripper left position controller. But anyway, let's plot right now. So let's plot the gripper left state process value and the command data. And it should act as before, because it's register wrong PID values. So in fact, if we press OK, now I remember you that this time the limits are between minus 0.05 and 0. And let's see what's happened, and you can see that there is still this wave behavior, and with an offset of around about 0.3. So we can do the same as we did for the gripper right position controller, and let's put the same value that we found for the gripper right. You can see that if we increase the proportional value, there is still this wave effect that is going to be cancelled with the adding of the integer value. It's not enough a huge value of this, but 10 it will be enough, as you can see. And then you can challenge your PID control. For example, if for both grippers we set 0, 0, the gripper is totally opened, and if for example for the gripper right we set an expression of 0.05 and minus 0.05 for the gripper left, the gripper should close. Let's check it. And you can see that it's closed, and the both state process value of the gripper right and the gripper left follows correctly without introducing any error the command data. So it seems that we have everything set up. We have spawned completely our six-axis robot with the gripper as well. Slider grippers for the moment is a good example, and we have tuned all the 6 joints plus 2 joints, prismatic joint for the grippers. And we can consider that it is a really good achievement, and basically we are at the end of our journey. So since that we have everything set up, feel free to play with your robot, sending a sinus expression to each joint and see how it behaves. And it's very important to see how the robot overall behaves by sending a different kind of command data topic. You can use an expression, you can use a scalar value. So let's try a little bit and make the windows in such a way that we can see the robot acting. Let's set an oscillation expression for the joint 4 position controller. As well for the joint 5 position controller, and we can keep the expression that we have set up in the last video. And for the joint 6 position controller we can set up at 0, and if we activate everything we can see how the whole robot acts. Every joint here is oscillating between minus 90 degrees and plus 90 degrees, which I think it's very nice to see the result of our work. Okay, now let's put to each joint a scalar expression. Let's set at 0 for each joint and see what happens. And it should go into the default position that we have set in our URDF file. So we have start with the joint 2, then move the joint 1. Okay, then we are gonna send to the 0 position the joint 3. Here you go. Then do the same for the joint 4. You see what's happening? The robot is going to the 0 position, so the joint 5 is going to reach the 0 position, and the joint 6 was already at that position. And here we go. From an oscillation behavior of each joint, we goes to a default position of 0 degrees for each joint. So meaning that this robot acts as we want. So let's make another thing, and let's set for each joint 90 degrees of angles, and to see at what position the TCP is going to go. So for example, we are going to set 90 degrees for joint 1, 1 radians for joint 2, 90 degrees for joint 3, joint 4, joint 5, and for joint 6 let's put a value of 2 in radians. Okay, so let's tip the windows, and the robot is going to the position that we have asked him to go. And this is an example of a forward kinematics where we have set up the joint position of each joint, and the TCP goes accordingly. So before to close, let's remember to update the YAM file for the gripper left position controller, and now let's test it again. Let's do another Forward Kinematics exercise by setting to all of joints a 0 command, and the robots will go to the standard position. Here we go. Joint 1, joint 2, joint 3, joint 4 is standing completely, and all the joints are correctly tuned, and everything is working properly and smoothly. So I hope that now you got the point, and feel free to try no matter expression that you want to ask your robot to do. So just put some random value for each joint and see for the last time how it behaves. And here you go. And then in direct we can see how each joint goes and the behaviors of each joint that is going to the setup command position. So, congratulations, that's all for today and for this ROS Control series. I hope that you enjoyed this ROS Control series and that you got a lot of technical value out from this. And if we want to make a recap, we can summarize in this PowerPoint presentation, where we have set up all the transmission tag for our joint. We have created the configuration file. We have set up the launch file to spawn not only the URDF file of our robot, but also each controllers that has been configured in the YUM file. And finally, you have learned how to tune the PID values of each controllers. You have seen how the proportional, integer and the derivative values affect the alignment between the status process value and the common data value of each joint. And with all this in mind, you have reached a good milestone that allows you to model your own robots and to control it using the ROS Control package, or better, the controller manager node of ROS. If you like this video, don't forget to subscribe to the channel and turn on the notification bell. And if you want to have more topic, and if you want me to go deeper in ROS Control, because there's something that you didn't understand, just write me in the comment down below, and I will reach you out as soon as possible. Another important thing is that in the description section of this video, I have put my GitHub repository, where you can find all the model, all the cobot simulation package, let's say. So feel free to have a look on that, check it out, download, and try to implement your robot with your ROS control. So, thank you for your attention, and keep learning robotics with ROS.